About 15 months ago, I gave a presentation on the possibility of building a propeller that would work in a vacuum. Today, I'll expand on the idea of exchanging momentum with the vacuum by adding pendulum tests and summarizing my research. I'm looking for collaboration on every level, and given the extraordinary claim, one must remain strongly skeptical. Let's take a closer look at the thought experiment. Consider a vacuum fluctuation as a pair of particles with opposite charges moving in the opposite directions. In non-uniform magnetic field, particles with opposite charges are deflected with different forces, and as a result, at the end of a fluctuation, momentum is transferred between magnetic field and the vacuum. We can look at here, the FA is larger than FB. We have to notice one thing, that accelerating the magnets will result in transferring momentum into the vacuum. And we can estimate the particle velocity based on the vacuum energy, and the distance traveled is driven by the uncertainty principle. Current physics disagrees with my assumptions, and the main violations are as follows. Vacuum energy is not a reservoir that you can tap locally without modifying space-time boundary conditions, and Lorentz invariance demands that the energy is isotropic. In quantum field theory, vacuum stress energy tensor in a static magnetic field is symmetric, and momentum density remains zero. Experiments that do show vacuum momentum transfers are fundamentally different from static magnetic gradients, and they involve time-dependent boundaries, moving mirrors, and radiation emission. And the big question is how the experimental physics could have missed an effect that contradicts Lorentz invariance and produces 200 micronewtons of force. Current physics versus new vacuum. Vacuum is not an elastic medium according to current theories, and static anisotropy alone is insufficient. We need time dependence, a boundary, or external gradient. What if the vacuum is an elastic medium? Then we could break vacuum isotropy, and in such case, the probability that the experiments I've done so far prove the possibility of building a vacuum propeller would be quite high. Given the current state of theoretical physics, experiments are the way to go. Here is a link to a recent paper hinting that the virtual particles are real transient particles. How to estimate the quantum force? Quantum force depends on gradient of the magnetic field, average x component of particle velocity, and vacuum energy density. Given the vacuum energy, quantum force can be obtained based on uncertainty principle and the Broglie wavelength. I'm not going to go over these equations, but the final answer is as follows. Thrust force depends on field geometry. Since we are considering the y component of the field gradient, as shown here and here, given the same strength of magnets, the two-base magnet configuration may result in higher quantum force than the three-base magnet one. The quickest and roughest estimation of the quantum force could be as follows. To estimate the total thrust force, QF, we can define the effective volume VE. Such volume has the same magnetic moment at every point. So in that case, integration is reduced to summation, and the n is the number of fluctuations in the effective volume. So based on the experiments, the following values were used in calculations. The effective volume was set to 212 cubic centimeters, and BA was roughly about 1 Tesla. We can estimate the quantum force using field modeling. We integrate over the volume. For every x on the grid, we sum up values along the y-axis, and there are two methods. The delta y method. In that method, y points and delta y are based on uncertainty principle given the vacuum energy density. In delta by method, with delta by being the difference of by between adjacent points along the y-axis. Thus, at the given point, the quantum force can be obtained as follows for delta y and for delta by. Different methods, different results. What vacuum energy density is required to achieve a given quantum force? And let's compare the three methods. For the effective volume method, we get the lowest energy required. For the delta by method, we get the highest. If we compare the delta by method with delta y method, we see that for the delta y method, we get a quantum force 100 times bigger compared to the delta by method. I have the following questions. Is the effective volume overestimated? Is the delta by method underestimated, or does it need a tighter grid? However, the final question has to be, is any of these methods valid? Let's look at vacuum energies. Minimum values required for quantum foam to contain particles with mass. I'll pick three values, 10 to the minus 9, 10 to 3, 10 to 26. 10 to minus 9 gives us a pair of axion-like particles with the rest mass of 10 to the minus 3 electron volts. So nobody has ever seen an axion. We'll see. For the electron neutrino, we have a mass of 0.8 electron volts and the energy is 10 to 3. For the electron-positron pair, with the rest mass of 0.5 mega electron volts, we have 10 to the 26. As fun exercise, I compared the repelling force between the magnets in the experiments to Casimir effect. So given 100 newtons and the effective area of 283 centimeters squared, I get 10 to the 4th. So that would correspond to the 10 nanometer distance between the plates in the Casimir effect. I have to make sure that it is clear that I don't think that bringing the magnets with the same poles closer together creates the Casimir effect. So looking at the values that support the results from the experiments, we have 10 to the 21st, which is fairly much lower than the energy required to create the electron-positron pair. But for the modeling results, we have values of quantum vacuum required much higher than the value required to produce electron-positron pairs. This value is high, however, is much lower than 10 to the 120 that results from the quantum field theory. But I don't really know what to think of these values and how to interpret them. Let's look at pendulum tests versus other tests. Beam balance tests. If you look at the results, they are very noisy. Torsion balance, the results are convincing. However, torsion balance is very sensitive to the interactions with the Earth's magnetic field. That's why setup L and setup R in these results had very strong negative bias. For pendulum, modeling enables estimation of the value of the quantum force. And when the direction of the QF is opposite to the motion of the pendulum, we are transferring energy or momentum into the vacuum, thus enhancing the effect. Let's take a look at the details of pendulum experiments, starting with gravity and friction. The horizontal component of Bob's gravity force, mg, determines the minimum value of QF that can be detected. And looking at the friction and resistance, we can use beam crossing times to estimate the friction. So the values that we use, the length of the arm was 1.5 meter, the Bob's weight was 130 grams, the initial swing was 0.3 degrees. That gives us value of 3000 micronewtons for the force of gravity. The smaller the x, the more significant influence of friction and mechanical errors. And based on the beam balance of experiments, the quantum force is on the order of 200 micronewtons. So if we compare 200 to 3000, that's a reasonable ratio. What is the influence of the Earth's magnetic field? Three forces acting on a magnet due to the Earth's magnetic field are as follows. Vertical torque, force aligning the magnet in the vertical direction. Directional torque, force aligning the magnet in the north-south direction, the compass force. This force is absorbed by the pendulum structure and can be minimized by aligning the pendulum swing north-south. And the third force is the force pulling the magnet towards the Earth's pole, and it is zero for all practical purposes because we can assume that the Earth's magnetic field to be uniform. So in conclusion, only the force related to the vertical angle, the dip angle, is of significance, and other forces are either absorbed by the structure or have very little impact on the swing times. Taking a closer look at vertical angle details. The force acting on the pendulum is proportional to the sine of dip angle plus swing, and values at the test location were as follows. Dip angle of the Earth's magnetic field, 69 degrees, strength of the Earth's magnetic field, 53.6 microteslas, and the maximum swing angle, 0.3 degrees. This picture shows how the forces from the magnets translate into the forces on the pendulum. So from this base magnet this way, and from the single magnet, force acting this way. If we flip the single magnet, the direction of the force would flip. So if you look at the direction of the quantum force versus the direction of the dip angle force, we see that for configurations as shown here, the direction of the quantum force is opposite to the direction of the force due to the single magnet. So the magnet configurations opposite to the ones shown above result in positive bias, that is, the direction of the force from the single magnet is the same as the direction of the quantum force. Here is how I measure swing times. Using ratios rather than direct values help to shield the errors due to sensor variations, and 2 microseconds is the minimum accuracy of sensor and hardware and software. So let's look how the measurement is done. We start here and we're swinging from the out zone to the in zone. We're passing the S1 sensor, nothing happens. We're getting to the S2 sensor, we record this value. We're swinging out to the in zone, coming back, and that gives us the in time. Moving back to the out zone, we hit the S1 sensor, going out and coming back, we get the out time. And the quantum force is determined via comparison between the NS and NS QFN configurations. So we have the NS configuration, we measure the ratio both in to out, and then we switch by flipping the single magnet to the NS QFN configuration, and we measure the values of the ratio between in to out, and we subtract the values. And based on the value of the subtraction, we see what the quantum force would be, and the value is determined based on modeling. Estimating the value of QF. Euler's energy time evolution method was used in simulations with the following steps. Model a single swing, use final potential energy of n- swing as the input to swing n, and keep n less than 20. Otherwise, the simulated swing period doesn't change much and there is little correspondence with the experiment. The time resolution was set to 10 microseconds, and that was based on IQR from the experiment. So if the quantum force exists, the following is to be expected. The NT to OUT ratio for the NS-QFN is expected to be higher than the ratio for the NS configuration, and the opposite is for the SN-QF-OUT configuration. The ratio of NT to OUT for the SN-QF out is expected to be lower than the ratio for the SN configuration. And that's what we see on the plot. This line represents simulation of non-magnetic wave, and the green line is the results from the corresponding experiments. So the force is determined based on the difference in these ratios, and that difference is linearized because I measured only 2 points, and the error introduced by linearization is way smaller than the error due to mechanical differences and noise and stuff like that. So it's all okay. Let's look at the test results. You see that for most of the configurations, these results are negative. And the main reason for that is that I used fairly strict pass criteria. And they're as follows. Both NS and SN magnet-based configurations are in agreement with the corresponding simulations, and the difference between NT and OUT ratio must exceed the standard deviations, or IQR, as I used IQR, more than 5 times. So my conclusion would be that based on the modeling, the value of QF is on the order of 200 micronewtons, and the value of 200 micronewtons agrees with 200 micronewtons indicated by the beam balance test here. So probability that such correlation is random is roughly about 0.1 to 0.8%. Here are the plots based on the tests. We can see that this is NS configuration versus QFN, and this is SN versus QF out. You see there is some variation between the tests, so that's why my requirement that these variations would have to be at least 5 times smaller than the distance between them, and this is satisfied here. Let's look at bad news. There's no free lunch, and let's look at the effects of moving the assembly. So we have here the assembly perfectly balanced, and let's see what happens if we move this to the outside by 3 millimeters or to the inside by 3 millimeters. And you see that the difference between the middle and 3 out or 3 in is huge. So assuming linearization of the effect, the minimum placement accuracy between the tests used to determine quantum force is required to be better or equal than 30 micrometers. That's huge. So let's consider the effects of changing the initial swing. The effects of changing the initial swing between 7 millimeters, which was standard, versus 9, and 7 millimeters versus 5 millimeters, we can see that there's a huge difference between those two. The 7 to 9, not that great, although significant, but 7 to 5, huge. So we say that initial placement of 5 millimeters is too small because the mechanical artifacts of the pendulum contribute too much noise. And assuming linearization of the effect, the minimum accuracy of the start swing is required to be better or equal to 250 micrometers, so which is not that bad. So let's look at yet another surprise. Oxygen paramagnetism. Forces due to the attraction of oxygen molecules. If we look at the simulation here, you see that these molecules are attracted to magnets, and the results, magnets are shifted one way or the other. So based on the configuration, we have a different results. So for the QFN, we have the pull to the left, and for the QF out configuration, we have a pull to the right. And we can see here that there is also thermal noise, but for thermal noise, the results are negligible. Okay, so force on the magnets due to the oxygen paramagnetisms is opposite to the quantum force, if we can see here. So, but one note, compared to the mechanical noise and positioning inaccuracy, the forces due to the oxygen paramagnetism could not be properly accounted for. But they're very small, and in the order of 1 to 4 micronewtons. Mitigating errors due to assembly placement. The difference in position of the magnet assembly between tests is the biggest source of errors. Pendulum's bulb is a V-shaped base where the magnet assembly is positioned. Two sides of the base were used in testing. Position blocker was used to ensure the same weight distribution between the tests. In tests without the position blocker, the assembly was adjusted to ensure the same rest starting position of the pendulum's arm. Field gap increases the influence due to the oxygen paramagnetism, yet it ensures better mechanical stability over the reconfiguration. So the tests with the field gap were more stable. So here are the drawings of the base and the whole position and stuff like that. And you have a position blocker and stuff and so on. So that's what about, and you have the dimensions of magnets and everything. Let's examine a run that didn't pass test criteria. So we have two runs, run 1 and run 2, and we have 3 tests per run. So if we take the average here and the average there, and we compare the difference in terms of micronewtons, we'd get these values. So for the quantum force that was detected of 100 micronewtons, we get the difference of 91 or 207. That's not very good. So this is bogus. Most of these tests are bogus except for this one. However, these values are correct, but the values for the QFN are not really trustworthy. So these values are considered garbage. So in order to get results that pass the test criteria, I had to run the test many times. Roughly 15% of tests pass the test criteria. What that tells me that the qualities, the mechanical qualities of my pendulums are not that great, and I have to accept it. So in conclusion, I have to say that as much as I like the pendulum experiments and as much as I think they're extremely valuable, I have to admit that I don't have resources required to build a pendulum that would satisfy the test criteria. In that case, next, I'm going to focus on torsion balance test. And as I said at the beginning of the presentation, I'm looking for collaboration on every level. Here is my email, and I thank you for your attention.